Welcome to another episode of the Common Babbler. And our guest today is Professor Dieter Suter. He's a distinguished professor of experimental physics at the Technical University of Dortmund, Germany. He works on quantum physics and magnetic resonance, and his work bridges the fundamental quantum mechanics with practical applications in computing and medicine. Professor Suter completed his PhD from ETH Zurich, and this was the Nobel Prize winning work group of Richard Ernst, and where the Fourier transform NMR spectroscopy was being developed. And Professor Suter is widely recognized for his work on mitigating the decoherence in quantum system, geometric physics in quantum physics, and quantum adiabatic algorithm for factorization. Currently, he serves as a master chair professor in USTC Hefei, China, and that is University of Science and Technology, China in Hefei. Welcome, Professor Suter.
Glad to be here. Thanks.
Thanks for dropping by for this conversation. You had a relatively busy schedule and probably a
Not
tiring
too
day.
bad.
No? Okay. You had been to India quite a few times and
That's right.
traveled quite extensively.
Mhm.
Anything very memorable?
Oh, too much to tell about, but my brief summary would be every time I find it amazing how many different things you can enjoy in India: the people, the geography, the culture, and the science.
You had been almost in last 20 years. You have been quite a few times.
Yeah, actually, it's probably, yeah, maybe 30 or so.
Oh,
Mm,
okay,
mm.
okay. And I think you visited Bangalore quite a few times, Delhi,
Yes.
Chennai, also Ladakh and Kanyakumari. So northern most and the southernmost tips of
That's
India.
right. Yes.
Yeah,
And the East and West.
and the east and west, of course, not to forget.
Mm.
Yes, yes. Your talk is on that tomorrow's talk is on. You call it the second quantum revolution and the future supercomputers.
Yeah. Well, that's this nomenclature is not my invention. This is what many people use for the type of research that I'm doing. Yeah.
So this supercomputer or the future supercomputers will be quantum computers.
It's at least the expectation. Yes.
I mean, of course, there is the idea, and I will probably ask you to elaborate the idea a little bit. And also, of course, it's quite challenging, and especially the robust supercomputers that we know today, which can operate at room temperature and relatively free, or how should I put it, relatively exposed to perturbations or disturbances. Would you please say how do you see that the idea of the quantum computation or computer, um, and then maybe we'll come to the challenges, the major challenges in the field.
Mm. So the basic principle of a quantum computer is that it uses more or less the Schrödinger equation, so the basic wave equation of quantum mechanics, to process information. And that brings, compared to traditional computers, which are essentially based on Boolean logic, that brings some additional possibility, and it brings additional challenges. So, as you mentioned, robustness is a big challenge because these basic concepts work well if you have a completely isolated quantum system. But the completely isolated quantum system is completely useless because you cannot put the information into that system, you cannot process it, and you cannot get the result out of that system. So there must always be a connection to the real world, where, because we are part of the real world, and if we want to get the results, we have to transfer the information into that real world. And as soon as you have this connection, you will have noise getting into this ideal system. And the issues are how to prevent this noise from destroying the information there. This is much easier in a classical computer where this challenge exists also. But first of all, it's easier there. And second, there has been work on improving that. So we have classical error correction has been improved over almost a century. And in quantum computing, we only have started that, well, maybe 20 years ago.
So, what are the, if I may ask, what are the advantages that?
It's the so-called scaling. So if you have a computation, say you want to add two numbers,
Hmm.
if these numbers get bigger, it takes more time. And if they're small, you can do it on paper and pencil. If they get bigger, you may need some time to do it on a classical computer. But no matter how big they get, the increase in the computer time that you need is known from the algorithm that used to solve this problem. So for adding numbers, this is fairly easy. If you have other problems like finding the prime factors of a large number, that the computer time on a classical computer increases exponentially. And that means if for a given size, there is always a certain size, no matter how fast your classical computer is, it will become impossible to find the solution within a time which is either smaller than a PhD thesis or the age of the universe. And if you do the same problem on an ideal quantum computer, this increase in computational time is much slower.
Mhm.
So you may be able to solve such a problem, which takes years on a classical computer, in just a few minutes, maybe.
And this difficulty of finding the prime factors is, of course, the basis of making our communication encrypted, all kind of secrecy.
It's one of the ways to keep our communication secure.
Mhm. So this for the quantum computers, this quantum object is electrons, which will have the desirable properties.
This can be different things. I mean, there are proposals and existing demonstrations which use electrons, which use nuclear spins, which use the charge of an electron
Mhm.
or the spin of an electron, or you can use photons. There are even things using mechanical resonators. You can use atoms or ions. It's basically unlimited as long as it's a system which obeys the laws of quantum mechanics.
So, in your view, I suppose that that is the problem that you are trying to solve in your research. Um, what is the interesting avenue among these systems that you are working on?
I refuse to make any prediction on that,
Okay.
and I don't think this can be answered in maybe the next 5 years unless we see a very fundamental and unexpected breakthrough.
Mhm.
And it may well be that there is not a single system, but it will depend on the type of application or say on the problem that you want to solve. For some problems, maybe ions will be ideal. For other problems, maybe nuclear spins or photons. Or it may be a combination. That's actually my uh, preferred way of working, to combine the strength of different systems into one.
I mean, of course, they will have. The reason I was asking, I suppose, is that, I mean, of course, it's my understanding that the nuclear spin states are relatively insulated. What you mentioned, that it's kind of slightly insulated from the real world.
That's right.
And that's where they also have this, I don't know if it's correct to say, but unusually long-lived quantum states, the nuclear spins.
Yeah. So
Um,
the longest uh, proven lifetime of a quantum state is on the order of 10 hours. And that
okay.
was on nuclear spins.
But also that also has limitations, clearly. I mean, that's why they are not I don't know. I mean, as you said, that it's still, the field is wide open and there are many contenders.
Yeah, the main issue is that you don't have to satisfy just one criterion. So the lifetime is one criterion, but there are many others, like the time it takes you to process the information and scalability. That is probably the biggest issue. It's useless to have a single quantum bit.
Mm.
So one nuclear spin is essentially one bit or one quantum bit. But to solve a serious problem, you need at least thousands of them, maybe millions, depending on the application that you have. And so, if you know how to keep one nuclear spin alive, but you don't know how to keep 100 nuclear spins alive, uh, the system will be useless.
This, for nuclear spins, or also for maybe electrons, uh, when from one qubit, one quantum bit, one has to go to, let's say, 10 quantum bits. Do the spins have to be coupled?
Yes. Well, you can, of course, have 10 uncoupled quantum bits or 10 uncoupled spins, but it's not useful
Right,
because to implement any algorithm, you need interactions between them.
right. So for nuclear spin, I can imagine to have that kind of coupling. It's already a restriction on the molecular geometry, that which kind of molecules can have that.
If you talk about molecules, but it doesn't have to be a molecule. And one relatively promising approach is to have, for instance, an electron which interacts with two different nuclear spins. And so that electron acts as a bus. So, like in a conventional computer, you have a bus which connects, for instance, the memory with the processor, and it transfers the information from one part of the computer to the other part. And so you can use this electron to transfer information between the two nuclei. So it's not itself used in the processing, but it mediates this coupling and therefore enables the processing of the whole thing.
Is that the idea behind the nitrogen vacancy
At least
system?
some kind of applications. I mean, in nitrogen vacancy, maybe you also want to use the electrons directly as quantum bits.
Okay.
That there are different versions being pursued.
So I listened to your talk that you gave in the conference. It was tutorial session, really.
And it was not on computing, but on sensing,
Right, right.
which is
And
another application of quantum technology
hmm,
and is maybe one of the most active results of this second quantum revolution.
okay, how so?
Well, because there are already many types of applications of quantum sensors. Maybe there it is a bit more uh, a matter of opinion whether you can label something as a quantum sensor or just as a good sensor.
Okay. So how and this nitrogen vacancy systems, or NV systems, are one of the promising choices there.
Definitely. Mhm.
And could you please So these nitrogen vacancy systems are in a carbon environment. There is one nitrogen embedded, and is that the right way to think about it?
Yes, there is a carbon environment, but there is also a nitrogen
Okay.
nuclear spin. Nitrogen always has a nuclear spin.
Hmm.
The carbon mostly does not have a nuclear spin, so the carbon 12, which are the normal carbons in diamond and in any carbon-based material, the carbon 12 is essentially invisible to the electron spin. So those you wouldn't count as carbons. You only count the carbon 13,
Hmm.
which in natural abundance are about at 1% of the positions. But in many applications, we actually reduce the amount of carbon 13. So it's maybe only 1 in 10,000 positions, which is a carbon 13.
So those are the visible nuclear spins. And so what's the role of the nitrogen?
So nitrogen is also visible, and you
Hmm.
can use it for your uh, quantum computing or quantum sensing. Uh, it's a bit more complicated than the carbon 13 because well, depending on the isotope, it can be spin 1/2 or spin 1.
Hmm.
If it's a spin 1, it means it has 3 energy levels rather than the 2 of a carbon 13, which gives you additional possibilities but also poses additional challenges.
So
As usual, there's always an additional possibility comes with additional challenges.
so this is the nitrogen 14, which will be spin 1, and the nitrogen 15, which will be spin half.
That's right.
But nitrogen 15 is also a stable
It's a
isotope.
stable, but again, in natural abundance, it's very rare.
Hmm.
It's much less than 1%. And so if you work with natural abundance, you normally work with nitrogen 14. But some people prefer the nitrogen 15. First of all, it's simpler. Second, it doesn't have a quadrupole interaction. And third, if you work with the nitrogen 15, you know it's one of the nitrogen atoms which you inserted yourself.
Okay.
So it's not there randomly,
Hmm.
but it's one of them which you actively implanted into the sample.
This will be a sample of, I know that you mentioned this is a carbon environment and you are inserting the nitrogen. So is it the artificial diamond or?
Yes. Also, you in principle natural diamond, but in natural diamond you usually have quite many of these nitrogen atoms.
Okay.
If you that you can see it from the color, by the way. If you have a very transparent uh, crystal, then there are relatively few nitrogen atoms. If you have a yellow one, you have more. But today, most people work with artificially made diamonds. They're grown with by some chemical processes, and you first make them as pure as possible. So in the ideal case, you don't have any nitrogen in it, and you add those nitrogens later by ion implantation. So you essentially accelerate nitrogen atoms, shoot them into the diamond, and then you have nitrogen centers. To get the NV centers, you need a vacancy next to the nitrogen. So you have to create these vacancies. That is partly happens already when you implant the nitrogen. So when you shoot the nitrogen, you create disorder in the crystal, and that includes these vacancies. If there are not enough vacancies, you can also irradiate the sample with neutrons, and that will create additional defects. Then you have to heat the sample so that the vacancies and the nitrogen meet. They have to be next to each other to create an NV center.
So these vacancies is like in a regular lattice, there should have been a carbon atom, but it's not there and there's a gap.
Yep,
So
it's a missing carbon
it's a
atom.
missing carbon atom. Okay. So this system, how is it used as a sensor?
Essentially, when you sense something, the best way of sensing something is to measure some frequency in the system.
Mhm.
And in this system, this is typically, it doesn't have to be, but in the typical case, you measure the transition frequency between two states of the electron spin. And this transition frequency depends on a number of parameters, like the temperature, like the strength of the magnetic field, like the electric field, or the pressure. These are the most common types of variables that you sense with an NV center.
For example, in a typical example in a NV center, depending on difference in temperature, the transition frequencies will be different, and that can be either the excitation or the emission of the from the electronic states that can be monitored.
No, you normally monitor the transition between the spin states,
Okay.
so not between the electronic states.
Okay.
So these transitions are in the range of a bit less than 3 gigahertz, 2.87 gigahertz if you don't have a magnetic field.
Okay.
This
So
is much more precise than if you measure the optical transition frequency, because the optical emission is rather broad,
right.
but the electronic spin transition is quite well defined, quite narrow. So you can measure that uh, with a precision on the order of a kilohertz or so, and you have shifts which exceed that quite quickly.
So this so a kilohertz level change in a base frequency of gigahertz. So is that in parts per million accuracy of
Yeah, it's below 1 part per million.
it's below 1 part per million. Okay. So that's where the extremely high accuracy comes in
Yeah,
for
I
the
mean, it's
sensors.
not the highest accuracy, of course. You have
Mhm.
now atomic clocks which have a precision at the 10 to the minus 18 level,
Oh.
but these are not solid state systems.
Hmm.
So for a solid state system, this is a pretty high free. Also, an NMR system has a higher relative precision.
Hmm.
You're now at about the ppb level in a good system, but that's a macroscopic
Hmm.
system. And among, yeah, so it depends on the application, but it's a relatively high precision.
And this kind of frequency difference and for the receiver in our electromagnetic spectrum that we are familiar with, which end will it come, or what will be the nearest identifiable sort of instrument or electromagnetic frequency that we are familiar with?
Well, I would say a microwave oven,
Okay. Mm.
or say a Wi-Fi network has frequencies in the same range.
Okay. And these, I think there were also subsequent talks or talk or tutorial which described that these sensors can also be used for medical as medical sensors.
Right.
Any example?
Yeah, for instance, one group or a combination of different groups in Germany just published a paper where they show that you can monitor the heartbeat with such sensors, which is not, I mean, monitoring the magnetic signal from the heartbeat has been done for decades actually, but with different types of sensors. So this is the first time, as far as I know, that NV centers were used for that purpose. Other groups are using it for monitoring brain waves. That's a much harder
Mhm.
target. And then it's used for measuring signals, for instance, from single cells. I mean, a big advantage of this system is that if your signal is large enough, you can get extremely high spatial resolution. The sensor has the size of a single atom. So in principle, for some applications, you can reach atomic scale resolution, spatial resolution.
Okay, so I mean, this is always a challenge in biology to um, get a very high resolution picture of a, let's say, cellular organelle
That's right.
under a microscope, let's say. But with this sensor, that might become possible.
Yeah, not just might, it has been demonstrated. For instance, people did temperature measurements inside living cells.
So cells communicate by quite a few messenger system, which is either an ion like calcium, potassium, in brain, of course, in neurons, it's a sodium potassium chloride. Um, can any of these sensors be sensitive to the particular nature, chemical nature of the ion or the concentration?
Well, not directly,
Okay.
but you can, in principle, for instance, functionalize the surface. So you put some molecules on the surface of the diamond, and if they, if you choose the molecules properly, they may bind, for instance, to calcium, and that will create a signal which can be sensed by an NV center.
Okay.
But the more common type of measurements is that you just sense electrical or magnetic fields, which you get, for instance, in a neuron when it sends an electric signal along an axon to another neuron.
Mm. And that will cause a transition and that can be measured.
Right. Mm.
Okay. Coming back from, or rather stepping back from biology and into medical application. So in which case I think one challenge will be to get the NV centers to the point that one wants to measure. Should it be in blood? I mean, can it be injected in blood, for example, or?
Yes, you can. That they're relatively harmless, but the problem is it doesn't help you too much if you have a diamond in the body,
Mhm.
because you cannot read the signal from that diamond, because the reading is done optically, and so you have to bring the laser
Mm.
to the diamond, and it will emit photons which you have to collect. And doing that would be rather invasive inside the body.
So that is a challenge.
Yeah, so these applications which I mentioned,
Mm.
like measuring the heartbeat
Yeah.
or measuring signals from the brain, this would be done outside the body. So
Mm.
you place the diamond next to the body, but not inside.
Okay.
There are also attempts to use it for measurement inside the body. One possibility is that you use the NV center to polarize nuclear spins. So you increase the polarization of nuclear spins, and if you're able to bring that polarization into the body,
Mhm.
which is already being done with other methods, then you can selectively enhance certain signals in an MRI image.
Okay.
So that would be very useful, but it's also highly challenging, and so far there is no clear path towards that goal on the basis of NV centers.
Right. I mean, this is of course a challenge in the typical magnetic resonance imaging, that the resolution is usually not great, not very high.
Well, the resolution is not the main problem. I mean, if you're patient, you can get resolution below 1 millimeter for a voxel, which is for most applications good enough.
Hmm.
But the main application of the type of experiments that I described would be not to measure with higher spatial resolution, but to measure more selectively.
Okay.
Say you don't want to measure just the geometry of a certain organ or say the geometry of a tumor,
Hmm.
but you would like to find out something about the metabolism.
Right.
So if the body has a problem, it usually changes the way it operates chemically. So some chemical processes in the body will be modified, and if you are able to inject specific molecules which are involved in these processes, then you can find out, for instance, where in the body this problem occurs. I mean,
Right.
say you measured from a blood test or so, you measured that there is some source of inflammation in the body, but from the blood test you don't know where that source is.
Mhm.
And so with this, you might be able to see it in an MRI image, and that would be very helpful.
I know that there has been quite a bit of development with these wearable devices. So maybe this kind of sensor, since you mentioned that there has to be a optical process
Yeah.
and it can be on the surface, there is some potential there, maybe in wearable devices.
That should in principle be possible. Uh, I'm not sure how far this is being pursued, but for instance, these brain scans, they they are in some sense wearable devices. So you put them around the head,
Okay.
and with other types of sensors, not with NV based, but with atomic vapor based sensors, this has been tested. So you have maybe 100 sensors using rubidium vapor in a kind of helmet, and with that you can walk around and people can monitor your brain while you're doing something. And you can call that also a quantum sensor.
Okay. Other than medical, what is the very exciting use of these sensors?
Well, you already mentioned biology. We
Right.
discussed neurons,
Hmm.
and there are also interesting applications in measuring, for instance, properties of magnetic materials,
Okay.
like two-dimensional magnetically ordered systems. You can measure say, if you have a hard disk, you have magnetic domains on them. They're very small, so you cannot see them by eye, and you cannot see them easily with other techniques. If you put such an NV into a small needle, you can scan across the surface and get a very high resolution image of such a device. You can also use it in principle to measure, for instance, if a chip works well. So you have an electronic circuit and you would like to know if the current through a gate, through a transistor, works as expected, and you can monitor that with an NV sensor.
Which is, of course, it can be very useful because chips very often have a high rejection rate because of imperfections, and so that can be improved.
Yes.
This is very fascinating about the sort of the scientific aspect of it, and I wanted to pick your brain about one more thing. Is and this is something that is fascinates me about where research is done and the universities. And you are, of course, in your career, you are familiar with universities in Europe very intimately. You have been familiar with the major institutions in India, including the Indian Institute of Science, TIFR, IIT, and IIT Madras, where you had been and you will be after Kriya, and ISERs. and you are now a chair professor, master chair professor in University of Science and Technology, China in Hefei. What's are they different? I mean, I know that at a certain level, of course, they are different, but um, I guess the interesting thing is that what do you see as the interesting features that make them stand out? Or
Well, in the end, it's the people.
mm,
And of course, it also depends on the resources which they have available. But in my experience, if you have the right people, they will always be able to make important contributions to research, teaching, and the society in general. And I mean, in some countries, it's of course easier to find the resources that you also need, but in all countries, it is possible to make some contribution. And very often that depends on the, say, connections to other institutions, to other people, because research is never something which you do just in your office, but it's always a collaborative effort. And the most useful, the most impactful research is in the end done by working with colleagues from different disciplines.
one question that comes up is so as an experimental physicist, sometime the setting up the laboratories is an expensive process. It requires a lot of investment. So that sometimes is one of the question is asked that what's I mean, and in comparison, some other research can be relatively less expensive. And also another debate I think that often comes up is that research in a research institute versus in an university, um, because sometimes the institutes are better equipped to carry out, especially for expensive research. And university has, and maybe perhaps it's also in the Indian system where universities are sometimes focuses more on teaching. Um, what's your view on this, or mm, how have you seen it in?
Well, I would say there are two somewhat related points that, I mean, you mentioned the price that you pay for setting up a lab.
Yeah.
And in that respect, I've never had problem to find the money, but that's partly also because my preference was always to build the equipment more or less from scratch.
Okay.
So that means you take cheap components and put them together in such a way that you make the experiment possible. And another approach is you buy the machine from a good supplier, and then you just have to turn it on and use it. So for some types of research, that's an excellent approach, but it was never the type of research that I was interested in.
Mhm.
So, and say the motivation for my type of research was to some degree that it's easier to find the money. Second, it's better for teaching because if you, and that there comes the connection to your second point, because the students thereby learn how such a machine works really
Mhm.
in detail. If they if they just use a commercial machine, they don't usually understand what the how it actually functions. And the third point is that this allows you to have fewer restrictions. I've encountered many cases where we discussed with, for instance, manufacturer of spectrometers about specific experiments that we would have liked to do. And they said, that's not possible, or this is not something interesting, or this is not something that anybody would ever want to do. So we decided to build the instrument ourselves. We did it, and a few years later, you were able to buy such instruments because it became obvious to others also that this is an interesting approach, which may increase the flexibility or whatever. And so to come back to the teaching aspect, which really interacts with that, doing that, building your own instruments, in my view, is useful, but you have to have students who are interested in doing that.
Mhm.
And that can be, well, for some students, this is very exciting. And so I've always had students who like that. And for instance, for them, it was quite easy at the end to find a job.
Mhm.
Because having the skills to build an advanced instrument is, of course, something that number of industrial companies want from their future employees. And so, as you said, these 2 points, these 2 questions are quite related to each other.
So you would say that certain way of doing research and teaching and training student can really go together.
Yes. Well, it
And
should. That's the basic mission of a university, in my opinion. I mean, if you're only interested in research, you shouldn't work at the university. You should go to a research institute.
right, do you think that research institute can be in some other way limiting, or there are some disadvantages of this model?
Well, I'm not sure about disadvantage, but I definitely think research institutions have a right of existence and
Mm.
they have their own mission. I don't know exactly about this country. In Germany, they do so-called targeted research. So at the university, most professors are free to choose their field of research.
Mm.
In a research institution like in Germany, the biggest research institutions are organized in the Helmholtz Society. There are political directions. For instance, most of them have a mission to work in medical research,
Okay.
which can, of course, be related to university research. And very often, for instance, some of our students work also at some of those research centers.
And you had been in USDC Hefei, you have been associated for almost 20 years. You have visited in
Well,
different.
yeah, in some sense, but most of my career only very loosely.
Okay.
But as time went by, we had exchange of students, exchange of professors. Some students worked in my lab for some time. They went back to USTC, they became professors, and now I'm a professor there.
Right. And you mentioned that it was a remarkable journey, that the university has really improved,
Yes,
doing excellent work.
it's amazing. I mean, when I first visited, it was only very basic. They had very little experimental equipment. Now it's much better than anything I've seen either in Germany or in India.
Okay. Fascinating. And your next sort of plans are from here to IIT Madras and then from there to USDC Hefei.
That's right.
It was wonderful have you here, Dieter,
My
and
pleasure.
looking forward to also having you in future in maybe another episode of the Common Babbler.
Okay.
Uh,
Thank you.
thank you, and thank you, and we'll be back with the next episode in near future.